This week, we're going to hear about how we make climate projections. I'm Peter Cox from the University of Exeter, but for many years I worked here at the UK Met Office, which is the world's leading centre for climate modelling. The Met Office is the UK's weather forecasting service, but it's also the world's leading centre for climate prediction. The reason that is because many of the processes that you have to model to simulate the weather over 5 days are similar to those that you have to model to simulate the climate over 250 years. The difference is that to simulate over 250 years, you need to take account of slower components of the climate system. Things like how ocean currents might change, how heat transport in the ocean might change, how the carbon stored in vegetation might change, are obviously relevant on long time scales, but are less relevant on the short time scales. So many of the processes are similar, additional processes are required in climate prediction, and you have to run for much, much longer, but similar models are used. Climate projections are made with climate models, which, like weather forecast models, break up the world into a number of boxes. We try to simulate how the temperature, humidity, and wind in the atmosphere, and how the temperature, salinity, and ocean currents in the ocean vary through time. And something like 2 million calculations are required every time step of the model, which is about 20 minutes. In many cases, we know the underlying equations that control the system very well. For example, we know the Navier-Stokes equations that determine how the atmosphere and the ocean move. In those cases, we just need a big computer to try and solve those as accurately as possible. In other parts of the system, like for example how vegetation and soil will respond to climate and how much carbon they will absorb, we don't really know the underlying equations, and it's much more of an art to determine what those equations should be. We do that by looking at data. Climate projection is a huge computational problem. Many millions of variables have to be updated for every time step of the model, which is about 20 minutes, for the entire 250 years of a climate simulation. And that means you need the largest supercomputer you can get your hands on, like this one at the Met Office. Even with a very large supercomputer like this, a typical climate simulation will take 3 months of elapsed time. So you really don't want to make a mistake and have to redo that again. So why should we believe these incredibly complex climate models? The most obvious way to test the model is to see whether it can reproduce aspects of the past that have been observed. So in the case of climate models, we try to simulate how the globe has been known to warm by about 0.8 degrees Celsius since the mid-19th century. And we do that by including the factors we think might have affected climate. These include natural things, like how the sun has varied in its output, and also when volcanoes go off, because they tend to cool down the climate system. But we also include human factors, particularly the increase in carbon dioxide that's been associated with burning fossil fuels and deforestation. When we put in the natural factors, we find that the models can reproduce aspects of the climate, but only until about 1970. From then onwards, the actual warming of the climate and what the models simulate diverge. And in fact, the models tend to have the climate cooling when it should be warming. But when we put in the human factors, particularly carbon dioxide increase, we find that models reproduce the observed warming extremely well. This gives us some confidence that the models are realistic. It also allows us to work out how much of the climate change that we've seen is due to human activities and how much is natural. This method of attributing the observed global warming to different factors is sometimes called fingerprinting. And it's fingerprinting that has allowed the Intergovernmental Panel on Climate Change to make quite definitive statements about the causes of global warming. They are able to say that there is a 90% chance that the global warming we've seen today is due to man-made greenhouse gases, and that is despite the uncertainties we have in climate models and in observations. So having convinced ourselves that climate models are believable, the next stage is to try to project how the climate might change over the next 100 years. And that's a different sort of a problem than predicting past climate, because whereas in the past we know how carbon dioxide changed, in the future we don't, for two main reasons. The first one is that we're not sure how carbon dioxide emissions from human activities will change. That's because we don't know how the population will grow, and we don't know how the way we generate and use energy will change. The second thing is to do with the natural world, which is we don't know how much of our carbon dioxide emissions will be absorbed by the oceans and by trees and soil that currently absorb about half of our emissions, but might absorb less in the future. These uncertainties mean that we can't be sure about how carbon dioxide and other factors that affect climate will change over the next 100 years, and we therefore have to look at a range of possibilities that we call scenarios. In order to project 21st century climate change, the IPCC developed scenarios based on storylines of how the world will evolve over the next 100 years. These include unknowns like how fast the population will grow and also how hard we work to combat climate change. As a result, these scenarios lead to very different amounts of carbon dioxide emissions in the 21st century and very different amounts of projected global warming, all the way from worlds in which we work really hard to cut emissions and to avoid 2 degrees of global warming, to worlds in which we get as much as 6 degrees of global warming over the next 100 years. So why should we care about global warming? Even to date, we see evidence that global warming is associated with increasing heat waves, increasing droughts, and even more intense hurricanes. And we expect to see more of that even at 2 degrees of warming. But at 6 degrees of warming, we're talking about warming of the climate by more than a change between the Ice Age and now, but 100 times faster. And when you push a system that fast and that far, there's a danger you cross thresholds that we call tipping points. These include things like a weakening of the Gulf Stream that actually keeps us warmer than we should be at our latitude in the UK, and could lead to the area getting cooler under climate change, and also things like collapse of the Greenland and West Antarctic ice sheet that could raise global sea level by 10 metres or more. Despite the complexity and uncertainty associated with projecting future climate change, we know that the planet is warming and we know that human beings are largely to blame for that. The big question now is how much the climate will change over the next 100 years and how that will affect human and natural systems.